Cool. So thank you for that lovely introduction. I'm going to be talking about improving PySpark performance today. So hopefully you're interested in PySpark. If not, that's totally cool too. You can zone out during my talk. It's all good. And so this is sort of, Spark is written in the JVM. And so this is focused on Spark performance beyond the JVM. I've done a bunch of things with Spark and other stuff. I'm from Canada. But right now I'm in San Francisco. I'm at IBM Spark Technology Center. And we are hiring if there's anyone else who is crazy enough to come from San Francisco to Amsterdam for PyData and you want a job, come talk to me. But I'm assuming most of you are not interested in moving to San Francisco. So I'll save you our normal recruiting spiel. The slides from today's talk are on my SlideShare. So if you're interested in seeing the slides or some of the slides from my previous talks. Maybe if you're not super familiar with PySpark already, I also have a previous introduction video at a previous PyData in Seattle, which I think is pretty good, but I'm pretty biased, so whatever. So I'm going to sort of cover a bunch of different topics. It's kind of a grab bag. I'm going to start with who I hope you all are, and if I get a lot of blank faces, we'll take some more time on some of the different slides. We'll do a sort of brief overview of Spark components, and we're only going to focus on the ones that really impact performance today. And we're also going to look at sort of the general architecture of PySpark, because it's kind of weird. And this really weird architecture actually has some really big impacts on sort of what things are slow. And then we're going to talk about Spark SQL. Which is the new amazing, wonderful thing which saves us from all our trouble except when it crashes. And then I'm going to tell you how to mix JVM and Python code for awesomeness. And it's more for minimizing sadness rather than awesomeness. You still get to write some of your Python code, but from time to time, if you're working in Spark, you do get stuck having to write some JVM code if you really want to get good performance. And then at the end, I'll wrap up with some cute pictures of cats and some key value data, sort of just general Spark things. They apply to PySpark as well, but they apply to scalable Spark just as easily. So I'm hoping you're all nice people. If you're not, I don't want to find out. Everyone here knows Python, right? Yeah? OK, I get a few maybes. So all the examples are in Python. I'm hoping you don't mind pictures of cats. If you do, you're going to have to ignore the top right-hand part of my slides. So this is my assumption that people know some Apache Spark. Is this true? Can you raise your hands if you know some Apache Spark? OK, that's pretty good. And for those of you that know no Apache Spark, you're still awesome, but I want to know how many of them there are. OK, cool. That's actually a pretty good mix. So for those of you that don't know any Apache Spark, there are going to be some acronyms that don't make a lot of sense. And you can ask me a question if it's just like completely out there. But after this talk, you might find it beneficial to watch one of my previous sort of more introductory talks. And then it'll sort of put a lot of these things in perspective. I think you can still get some good value from it because it covers some interesting architecture stuff. And I'm assuming everyone's here because you like performance. If you're working with kilobytes of data, it's cool. You can probably just go and grab another coffee. It's not going to be a big deal. So that's my intro. And there's another picture of a cat because I love cats. But so what is Spark? For those of you that have no idea what Spark is, it's a really awesome general purpose distributed system. A lot of people come to Spark just because they're looking for something faster than MapReduce, which is a really low bar, but it's a really low bar Spark jumps over. For a lot of things, it can be like 100 times faster is the standard benchmark, which is probably about as true as your average vendor benchmark. But it is actually much faster in a lot of production jobs as well. But I think one of the really nice things about Spark compared to like traditional MapReduce type systems is the API is so much more expressive, and it's really wonderful, and you're not stuck trying to like cram all of your things together into mapper and reduce tasks and doing a bunch of really weird things to get reasonable performance. We have to do some weird things, which we'll talk about today, but not nearly as many. So there's all of these wonderful components, and today we're going to be focusing on the Python APIs and SQL and DataFrames. For those of you that know pandas, don't get your hopes up. Spark DataFrames are not pandas DataFrames. I'm sorry. But they're really cool, and they do give us sort of a DataFrame-like view into our data. And these different pieces of Spark, they all ship together, which is really convenient as users. So if we want to do some machine learning after we've done some sort of SQL transformations, it's really easy to make these systems work together. We don't have to save it out to another system and launch yet another distributed computing system. It all works together. And also, because these are all developed together, a lot of Spark's performance comes from sort of improvements that were made in different components. So for example, streaming had to really, really lower the task creation overhead so that it could run really quickly for its micro batches. But this benefited SQL as well, because you have this much lower task overhead that was necessary for streaming to be successful, but it also benefits SQL, especially for small queries. So let's look at how PySpark is made. It's not nearly as fun as this playground. It's actually pretty sad. So Spark is in Scala. How does PySpark actually work? It uses Py4j. Has anyone here used Py4j? My condolences. Unless the Py4j maintainers here, in which case, I love you. It uses Py4j, pickling, and a fair amount of magic. And this can actually be really slow. The RDDs, which are the Spark's way of representing distributed data, are RDDs of pickled objects, which is kind of painful, right? You're having to serialize your stuff, shove it into the JVM, and then shuffle it around. And Spark SQL is pretty cool because it sort of avoids some of this problem. We don't have to shuffle around pickled objects. We can actually do our operations on JVM objects, and this can be less painful. But this is sort of what the world's worst architecture diagram for PySpark looks like. So on our driver program, we have our Python interpreter, and it's calling the JVM over Py4j. And then our workers, we're using Unix pipes to send data from the JVM to our worker Python processes, which is kind of slow. It's not as slow as writing it out to disk and reading it back in, but it's not exactly fast either compared to just keeping the data inside of the JVM. And yeah, so the double serialization cost is really the expensive part about this. And the biggest takeaway for working with PySpark is we want to try and avoid this double serialization cost. Surprisingly, for distributed systems like Spark, a lot of our time is spent just serializing our data. Our actual computations themselves are frequently not the big blocking part. A lot of it is just serializing stuff and shuffling things around. Not exactly directly related performance-wise, but for those of you who have used PySpark, you might have noticed that the error messages make no sense. It's not just you. The error messages make no sense. I'm sorry. We should fix it someday. OK, so that was the sadness. Let's look at how we can make this happy, like this cat. So this wouldn't be a big data talk if I didn't have word count. And I like keeping my big data license, so I'm going to give you word count. So for those of you who aren't super familiar with Spark, the first bit is sort of loading our data in, and this is lazily evaluated. And then Spark is able to sort of chain the additional operations together and do some sort of intelligent stuff for us. And once we perform this action, Spark actually evaluates all of the transformations that we've done and has to do its thing. One cool thing to note is while we do have this double serialization cost, we don't pay it on like a per operation basis. We pay it whenever we get to the point where Spark can't pipeline things together, right? So this flat map and map, they're going to get pipelined together. So we don't have to worry about like adding more maps and try and do the crazy things that we were doing in the Hadoop world for good performance, right? We do our map, and then we do this reduce by key, and then, OK, yeah, we get hit again because we're having to bring our data into the JVM, shuffle it around, and write it back out to the workers. But in theory, DataFrames are going to fix this for us, right? So that's wonderful. We can keep our data inside the JVM, but we can still write Python code. And so that's a pretty good win-win. It takes our Python code and it gets converted into a query plan, and it's pretty good, you know? They're not pandas or R data frames. It helps if you lower your expectations down to SQL, and then occasionally you get surprised when there's slightly more there. But the really nice thing is if we have some really like massive data problem, right? Frequently we're only interested in the subsets of this data for our actual analysis. So if we can do our initial filtering or our initial sorting using data frames and then do the subsequent work with RDDs, we're able to get like much better performance than just doing the work in RDDs. Because the initial big expensive part is happening all inside of the JVM. So essentially what happens is our really nice Lambda expressions get replaced with these SQL expressions. And that's okay, right? But you know, you probably don't want to do this unless we actually get good performance from it. So what does data frame performance look like? So compared to groupByKey, amazing. But groupByKey in Spark is pretty much the devil. So that's not all that impressive. But you know, we would probably write something that was doing a groupByKey with a reducedByKey anyways. And we can see that data frames still outperform a native reducedByKey. And this is computing the average on some columns. I don't remember how many. It might have been like 5 or 6. But this is just a really simple computation. And you can see that it still outperforms even inside of Scala. And inside of Scala, data frames aren't saving us from this double serialization overhead. They're just saving us from writing terrible Scala code. So this improvement is even bigger for Python. So we should try and rewrite word count so that it's extra fast and that our 100x benchmark that we show to people can be a 200x benchmark. But we don't have a way to split our words. There's no SQL thing implemented to do that really easily for us. So we could do a few different things. Data frames can go back to RDDs really easily. So we could do that. We could make our data frame, take it into an RDD, and then switch it back to a data frame. That's about as fun as it sounds, which is not very. We could write a UDF, or if we were in Spark 2.0, which doesn't yet exist, but will very soon at some point, we could use datasets, which are really awesome, and they let us sort of write these functional style transformations while keeping our data in a data set, so we don't have to convert to an RDD and back. So, data frame to RDD and back again. We can just write a standard map transformation. Converting it back, we could have Spark automatically infer the schema for us, but that's going to be kind of expensive. So instead, we know what our schema is, so we can just specify the schema. So word count with data frames, I didn't specify the schema here because it doesn't fit super well onto a single slide. But word count with data frames looks pretty similar. We have our flat map. And our flat map is still going to have this double serialization cost. But when we're doing our actual shuffle down here, we're doing our shuffle on JVM objects. And we're not doing it even on like just raw JVM objects. We're doing it on these really cool objects that in their serialized form are actually comparable. So it's super happy. Spark SQL's data formats are really awesome. And so this computes our word count using Spark SQL. But we still do pay some of the double serialization cost, and we want to get out of that, right? So what can we do? We could make a UDF. Turns out, if we make a UDF, we still pay the double serialization cost, but we can feel nicer about it. So that doesn't really do a lot for us. But we could actually make a Java UDF instead. This is a little sad, right? Because I'm essentially telling you to get good performance for PySpark, we need to do some stuff in the JVM. But it's not that bad. We write some Scala code. It's if you do it for the parts which are really expensive and you keep your Python code for the parts which are really awesome in Python, I think it's worth it, especially when you consider the fact that you can really easily use UDFs from things like Hive or existing libraries. There's a ton of like Spark Scala libraries, and if we're willing to play sort of fast and loose with accessing internal members, we can get really good performance. So let's go ahead and start playing fast and loose with accessing some internal methods. So we'll start that by creating evil SQL tools. And evil SQL tools will let us sort of get at the underlying components of a Spark column. And this is useful if we want to pass a column in rather than creating a UDF and writing some SQL statements. So essentially, we could call kurtosis on a column name rather than going .sql select kurtosis. I mean, they're both fine, but one of them I get to have something that starts with the word evil. So I like evil. But now we need to actually be able to call these functions that we wrote in Scala for us. Most of the things have _j object type, and that gives you the Java backing object. So if we want to pass in an RDD to a Scala function, maybe someone has a really awesome Scala Spark library, we'll just pass it in rdd._jrdd. And I mean, df is ._jdf, and so on. The catch is, right, these things are all internal methods, so if we go ahead and use these, it's probably going to explode at some point in the future, but for at least the next several months, you'll get much nicer performance, and someone else will be stuck maintaining your code once you quit and get a better job. Or at least that's the American way. The one catch is the Py4j bridge only exists on the driver, so we can't, with the notable exception of Spark streaming. But so we need to call our methods on the driver rather than trying to call them on the worker. And if we try and call them on the worker, it'll just explode at runtime with an error message that makes no sense. But so this is how we start and actually go ahead and call random methods on the JVM. So our Spark context has this _JVM method, and then we can just go and type the full path to our object. So in this case, it's from a project that I worked on called Sparkling Pandas, which is a project for making pandas like DataFrame interfaces in Spark. And so we have a function called register UDFs, and we just go ahead and we go ._JVM com sparkling pandas functions register UDFs, and I pass in my SQL context so that it can do its work. And we could call this on a column for the kurtosis function, and we can call this on really almost any object that we're working with in Spark. So that's cool, but maybe I haven't convinced you. I'm seeing a lot of people that don't look like they want to go home and write JVM code. And in retrospect, Python conference should have been obvious. Not going to be a really easy sell. So I mean, let's say we just want to work with DataFrames and we don't want to go ahead and access crazy internal things. What sort of things do we need to do so we can get really good performance from DataFrames? There's a bunch of things essentially that we just don't want to do, and then we're going to get good performance. One thing is we don't want really, really huge schemas on our DataFrames because for some reason they're serialized as JSON data and passed to the driver program and back, which is OK for medium-sized DataFrames. But if you start having a column for every individual user, that's going to not go so well. So don't do that. The other one is there's this really awesome function on DataFrames called toPandas, and it lets us take a Spark data frame and get back a pandas data frame. The thing is, toPandas is essentially collect. What it does is it takes our wonderful distributed data frame and it brings it back to our local node, which promptly falls over because we tried to bring back 80 gigs of data to an 8 gig laptop. So don't call toPandas unless you're really, really sure you've actually filtered it down to some small data. Another one is it's really easy to accidentally do the cross product of your data in Spark. And the cross product of a big data and a big data is an out of memory exception. So when you're writing your joins, it's really important to actually think about what you're joining on. And if you're joining on something which maybe has a null value, maybe 80% of your keys are null. It's actually going to do the cross product for all of the things which are null, and then it's going to explode and fall over. So you should filter out those null values before you do your join. Another thing is, if you're like a really experienced RDD programmer in Spark, DataFrames have like some little weird quirks to them. They're not quite as lazy as RDDs, right? So as we're doing our transformations, Spark would normally not give us any sort of error messages as to what's going on. But with DataFrames, when we're loading our data, it sort of infers some schema information. So if we try and load some data that doesn't exist, it's going to yell at us. Or if we try and select a column that doesn't exist, it's going to yell at us. And I mean, those are all probably good things to find out about sooner rather than later. But it's something to keep in mind. So why is groupByKey so slow anyways, right? Back on the first slide when I was trying to convince you to use DataFrames, I said, this outperforms groupByKey, but that's not actually, all that impressive. How many people think groupByKey should not be terrible? Okay, that's a good number of people. I tried to convince people of this once inside of Spark, that we should actually wrap the groupByKey API in something that went over like a lead balloon. But I'm optimistic that some year I'm going to get people to change their minds. Most likely, actually, what's going to happen is DataFrames and Datasets will take over, and this won't matter. But for now, groupByKey is pretty much the devil. It's really easy to make groupByKey fall over, and it's important to sort of just remember that while groupByKey performs really badly, a lot of the problems we can get with it, we can get with other operations. So, what are these problems? Essentially, once we start working with key value data and we start trying to do operations, we should actually think about what the distribution of our keys looks like. That's probably sort of natural to a lot of the data scientists in the room, but maybe for some of the data engineers, you're not used to thinking about like what the distribution of your data looks like, or you don't have a very intuitive understanding of how many orders happen on Tuesdays, and you try and do a groupByKey by day of week. We should think about what type of aggregations we want to do, and we also need to think if we need our data in any particular order, could this cause a problem? And it turns out it can actually cause a problem. All of these things can cause problems. So how do they cause problems? So key skew. Everyone's had data with key skew if you've worked with real data. Sales by postal code, records by city. We can have unbalanced partitions, and then that's OK. Our Spark job will look like it's going along. It'll chug along, and we'll have some stragglers, but it'll succeed eventually. But we can also end up with partitions that are just too big for Spark to process. And we can end up with records which are too big. Right. So groupByKey is pretty evil. And what groupByKey actually does is group all of the records with the same key into a single record, even if we immediately do a reduction on it afterwards. So even if we do a groupByKey followed by a sum or really anything, Spark isn't able to introspect the second lambda expression we're providing it. All it knows is that we asked it to do this groupByKey. And this is sort of one of the limitations of the RDD API. And this is one of the benefits of using the DataFrame API is Spark is able to better understand what we're asking it to do, and it's able to see that while we've asked it to group this data together, we then did a reduction on it, and it can actually understand that it can pipeline this reduction and start doing really awesome things for us. So, right, unless we're in SQL, then happy pandas. So this is what the explosion looks like. 94110 is a zip code in the mission. So this could be handlebar mustaches, which are very popular in the mission. I notice a complete lack of handlebar mustaches here, which is a little bit depressing, I'm going to be honest. So, word count with groupByKey, we could write it this way. And if we didn't know that groupByKey was the devil, this looks like a pretty reasonable way to write this code, right? And the normal version is pretty simple, right? All we do is we replace our groupByKey with a reduceByKey. And the reduceByKey tells Spark, like, hey, what's up? Actually, I do want this information on a per key basis, but this is the aggregation that I'm going to be performing. I'm going to be like summing these two values together. And I mean, this is a pretty simple aggregation, but we can express a lot of other aggregations. So we can compare these two. Like maybe you don't believe me. Maybe you think groupByKey is actually implemented really amazingly. So we could run this code. Oh crap, I forgot to replace this one with Python. Sorry. A little bit of Scala code. But we could run these two, and we can see, I'm working on kilobytes of data because I wanted the job to actually finish. But with groupByKey, we have a shuffled write of 424 kilobytes and a shuffled read of 48 kilobytes. With reducedByKey, our shuffled write is actually all the way down to 376, and our shuffled read is 11.6. So why did we get these smaller numbers? So we replaced groupByKey with reducedByKey, and one of the really awesome things about Spark is, unless we tell it otherwise, it sees a reducedByKey or an aggregateByKey, and it says, hey, what's up? I'm going to reduce my data before I even start shuffling it. So essentially, we get a free map side combined. What happens is each worker goes and finds any duplicate keys, applies the reductions it can locally, and then it does a shuffle. Now, if we know, for example, that our data, there's no point in doing that, right? Like we're doing a groupByKey, or we know each partition has unique values, we can tell Spark, no, what's up? It's cool. I know better. Don't actually apply this map side reduction. It's cool. So the reason why we saw these smaller shuffled writes and reads is that we were essentially reducing our data beforehand. So not only did our job have the chance to succeed, it also took less network bandwidth and took less time. So one thing that I sort of skimmed over was that we read in Python star.py. And this is, instead of the standard, my favorite one is reading in the README file, which is also kilobytes of data and finishes very quickly. But the README file doesn't have enough duplicated words to actually show a difference, right? And this is the case where groupByKey, while it's the devil, if you occasionally want to worship the devil, that's cool with me, but know your data distribution first, right? If you have mostly unique keys and the ones that are duplicated aren't duplicated all that often, groupByKey is okay, but you should probably still be a good person and use aggregateByKey. But if you're going to go ahead and use groupByKey, I'm not going to be around to tisk at you, and Spark isn't going to fall over and lose all your data. So it's okay. But just remember what your data distribution looks like. So that's cool. What about if we just wanted to sort our data, right? I'm interested in seeing sort of all of the people that are in the same zip code. I want to know where the handlebar, I want to see all the people in the same zip code who have handlebar mustaches. So I'm going to sort my data. I'm not going to group it together by key, because I got told not to do that. So I know that's a bad thing. But it could still explode if we tried to do our shuffle, right? Our shuffle explosion looks like this, right? While we don't have this massive key, we still get a partition which has too much data in it. And too much data is sort of a relative term, but we'll pretend it gave us an out-of-memory exception, right? Handlebar mustaches probably wouldn't do this, but if I tried to sort sales by zip code, there's a really good chance that I'm going to just actually make Spark fall over. But this is a really legitimate question to ask, right? I have some information, I want to sort by it. What do I do? So there's a few different things. Oh, okay. The really lazy answer is we just append some junk to the end of our key. And that works. What'll happen is Spark is smart enough that it actually samples our data and uses this to determine what the partitioner should look like. So we just need to give it a way to split this data, and it'll do it for us. The downside of doing this is if we do a join afterwards, our join is not going to have a really good time. But we can just add some junk to the end of our key, or we could even add some of the value to our key, and our shuffle would be fine. So switching topics pretty much completely from key value data to reductions. Spark reductions are actually kind of frustratingly naively implemented by default. It reduces the values per worker and then sends all of those values to the driver. Does anyone see a problem with that? No. OK, well, that's fine. And if you have 5 workers, that's probably OK. But if you have 500 workers and you're getting these really big values, you might want to actually try and apply your reduction in sort of a staged method. So we reduce the values per partition, and then we combined adjacent partitions together, and then we finally send those results back to the driver. This isn't like really something that you're probably going to need to do very often, so don't just go out and replace every instance of reduce with tree reduce. But if you're doing something like computing maybe the residuals from a machine learning model on a lot of nodes, this might be something that would make sense to do. And you can sort of specify how deep you want this tree to go, and you can play with that parameter. So I did say I would talk about RDD reuse. And really the sad part is that unlike this cat, RDD reuse is not magic. So in Spark, Spark is amazing. Lazy evaluation is like my best friend. But sometimes I want to use the same data twice, right? How many of us read in data and then we want to use it more than once? We want to perform like 2 actions on it. OK, good. People haven't fallen asleep entirely. That's great. So quite a few people, right? And there's a few different things we can do. We have to know which ones we want to keep around, and we have to tell Spark to keep these ones around for us. So we can cache it. Caching is great when our data fits in memory. But probably the reason why you're using Spark is your data is really big, and it might not fit in memory even across your entire cluster. And maybe you need to cache multiple things, right? Maybe you've got a users table, and you've got like all of your sales tables, and then the marketing people show up, and they've got another table they want to cache, and eventually you start to find things getting evicted. That's OK. Like Spark handles these evictions gracefully. It'll just recompute the bits of data as they're needed, but it can be useful to actually just have Spark write it out to disk as well. And if our computations are really expensive and our clusters are noisy, how many people have clusters where you lose nodes occasionally during your jobs? OK, a good number of people. So for those of you who work on noisy clusters, maybe the AWS Spot instances, it can be useful to cache to multiple machines so that if like some of our machines get killed, we don't have to recompute that part of the data. This is especially true for things with shuffles or what's called wide dependencies. So in Spark, if we use a map transformation, it creates a narrow dependency. And this is our partition output depends on a set number of known partitions inputs. So when we need to recompute it, we know which pieces we need to go upstream and recompute. But if we have like a shuffle, I might depend on recomputing all of the previous data, even if I only lost one partition downstream, right? And so that can be really expensive, especially if you had like a lot of work going in to computing the data before that shuffle. And if you're on a really noisy cluster, you can try checkpointing. Checkpointing essentially gives you the MapReduce hammer of writing everything out to disk, and it gets rid of using Spark's recompute method. And this normally isn't a good idea, but if you're on a really noisy cluster and your data is really expensive to recompute, checkpointing is actually a really good technique. Checkpointing is normally used for when we've applied so many transformations to an RDD that it becomes difficult for Spark to keep track of them. But it can also be used for when our cluster is just really, really unreliable. Like if we've bid 20 cents on our AWS Spot instances, it's probably a good idea to do checkpointing. So probably a good reason why you want to use PySpark is you've got some libraries that you want to use. And this isn't really performance, but how many people are using Python with libraries that don't ship in just the standard Python, right? That's everyone. OK. How many of you have all those libraries installed on every single node in your cluster? OK. 2. So your code runs, and that's great. But for the rest of you, you probably occasionally have the sadness when you have some distributed code, it depends on some library, and then it fails, and you're like, oh, crap, I forgot to install it on this machine. That's pretty cool. Right, OK, sorry, yeah. So there's a few different things we can do. If our generic Python library comes in a zip or egg file, we can distribute it. We can use --zip files or just the add py file function on the Spark context to distribute our library. And so that's really awesome, except it doesn't work for many of the libraries that we care about, which is a little sad. Another one is if someone gave you the root keys to your cluster, you can use PSSH and install your libraries on all the nodes. And it's a little sketchy and kind of sad, but it works. And the other one is the CDH plus continuum plus anaconda equals approximate sanity. So there's some really cool stuff from the Cloudera people, and they make it really easy to use anaconda with CDH, and you can install your packages. This replaced a previous bullet point which said, sadness and crying. So approximate sanity is a great improvement. Yeah, so this wouldn't be a talk if I didn't try and pitch you on a book that you should clearly buy 6 copies of, one for home, one for work, and several just to throw in the dustbin. But I'm working on another book called High Performance Spark. I think it's pretty cool, but I'm obviously incredibly biased. The examples are really Scala-centric, but if you care about Spark performance, I think it's still really interesting even with the Scala-centered examples. And there is a section that's going to be dedicated to working beyond the JVM and sort of the things that you need to do to survive. And we'll eventually port the examples to Python in my copious spare time, which I'm sure will happen this year, probably. Don't hold me to it. But if you feel like giving me your email address to spam@highperformancespark.com, and I will spam you mercilessly as soon as you can give O'Reilly money for the book. And there's also a Twitter account, which I forgot about until I saw this slide. So you could also follow that account on Twitter. Yeah. And actually, we'll probably be having an early release of the first 4 chapters later on this month. Although, admittedly, we don't get into any of the Python-specific stuff yet. But a lot of the sort of the general techniques, as well as sort of some examples of how to work with DataFrames are in there. So I think it's cool. I've got a bunch of Spark videos, and there's a whole bunch of Spark videos from people that aren't me. I think Paco's Intro to Spark video is amazing. If you're not just interested in learning specifically PySpark, I really encourage you to check out Paco's videos. Yeah, these links are in the SlideShare if you want to take a look at it, or you can just search for Paco's Introduction to Apache Spark. He also, if you have a corporate credit card, you can buy his Intro to Spark video, but it's also for free on YouTube if you don't have a corporate credit card. But the fancy O'Reilly one looks nicer, and you should support Paco if you have the money. I'm also going to do office hours. So this was sort of a random grab bag of topics of things that I hope people might find useful. There's a good chance that what I was talking about wasn't particularly useful to the stuff you're working on. But you can come hang out with me at the Booking.com offices, wherever they are. I need to find that out. Tomorrow at 6 p.m., and you should sign up on the meetup so security people have their list. And you can ask me any Spark questions, and I will give you an answer or not, depending on if I know it or can figure it out. You should also follow me on Twitter or LinkedIn. I mostly have pictures of cats and complaints about American healthcare on Twitter, but I do occasionally talk about Spark, and LinkedIn is very much business numbers. So that's my K thanks, bye. There's a cat that says bye.
So being a cat person as well, I have to compliment you on the final slide, because it does add sort of an extra nice little thing to the whole talk. Thanks for the talk. It's always good to have like an in-depth talk on technologies that everyone here is using. Are there any questions for Holden? As Holden's mentioned, there's always the office hours, but I see there's someone in it. 2 people. Gotcha.
Actually, I have a couple, so I'll come by afterwards. But let me ask at least one about the GroupByKey.
Yeah.
Sometimes you don't want to aggregate it. You want to group the data, but you don't want to aggregate it. So what would you suggest if not a groupByKey?
If you want to group your data, but you don't have a subsequent reduction or aggregation to perform, doing a shuffle, possibly doing a shuffle while adding some junk to it, and then you can use map partitions to process it on a per partition basis, and essentially manually do your logical processing that way. It's really nasty. I have an example of doing it for high performance Spark. It's in Scala, but the same logic applies. It's a little ugly though, and I'm sorry.
There's something that's called Jython,
Yeah.
which is not in a wonderful state, especially when combined with Python 3. But knowing things about Scala and Spark, do you think it could be a viable approach to reevaluate that option?
Sure.
Compiling Python to JVM and then accessing natively all these objects instead of doing this double serialization?
Yeah. If Jython worked well with libraries that people cared about, I think that would change the conversation completely. But I think realistically right now, using Jython just really wouldn't be that beneficial because most of the libraries that people are really, frankly using Python for aren't there. I looked at doing some stuff with it, and when I was working on Sparkling Pandas, not inside of Spark itself, and it just wasn't there. But I mean, if that changes, the Spark people are definitely open to changing things, especially in the language APIs. There's a fair amount of flexibility there.
So I think we might have time for one more final question, if there is one.
Oh,
Yes.
Thank you for the talk. I wrote a note about Spark 2.2, and you mentioned we won't expect DataFrame anymore in that version. Or I misunderstood that one.
Okay, the question was Spark 2.0 don't expect DataFrames anymore?
Yeah, I wrote something like that.
Oh,
but
no.
Could you please elaborate on that?
Don't worry. So DataFrames will continue to exist in Spark 2.0. Datasets are coming as well, though, and they make it even easier to intermix functional and relational style programming. So essentially, if we look all the way back here, right? After I did my flat map, I had to manually convert it back to these row objects, and that's kind of janky. And essentially with datasets, we're not going to have to do this really janky stuff. It's just going to work for us, and that's going to be lovely and wonderful. But we can the DataFrame API will still be there. The dataset API is just sort of building on the success of DataFrames. Cool. Thank you so much for having me and putting up with my occasional Scala code, and I'm very sorry about the Scala code.
I think the Scala code is just fine. Please give another round of applause for Holden and Boo.